All right. Welcome back, everyone. I am very proud that every single one of you managed to enroll in my math lab. I don't get to say that too often. I'm hoping that I can get a perfect, I can't call that attendance, perfect enrollment in my math lab this semester on time. That's my goal for the semester, I guess, initially. So we are going to pick right up with material, and we're going to start in 5.1 today. So we've already talked about the course. If you have any questions or confusions, you can always email me, but we're going to stick to material today. So this is a class all about trigonometry. So we are going to study trigonometry, and let me just kind of take some of those away for now because I'm going to be doing some drawings on the screen. So 5.1. Angles and their measure. The text actually changed the title to Angles and Radian Measure, but that's fine. Doesn't matter. One thing I want to point out, if you ever see an incorrect section number, that is from us changing texts and additions numerous times over the past 6 years. I'm generally pretty good about having it correct as I'm going along, but I might accidentally refer to this as 7.1 or 6.1 because this chapter has been chapter 6 and chapter 7 in various textbooks before. All right, so angles and their measure. The first thing that we're going to talk about are rays. A ray is a part of a line with only one endpoint. So if you've been in Pre-Calc 1 and previous courses before that, and you know what a line is, a line extends infinitely in each direction. But a ray does not. A ray is just an endpoint, and then it extends forever. And it doesn't have to be pointing up and right. It can point in any direction like a clock. So that's a ray. It's part of a line with only one endpoint. Now, for the first couple times today, I will draw these little dots, they're endpoints, but moving forward in the class, the rest of the semester, I really won't ever draw those dots again because it just gets tedious. That's your ray. An angle is a measure of something. You can't really call it a distance, it's just the measure of kind of the relationship of one ray to another based on their positions and how they're opening up. So an angle is formed by two rays with common endpoints. So that point is what we call an endpoint. So this is two rays with common endpoints. And then we can say that it has an initial side and it has a terminal side. And that common endpoint has a name. Actually, we'll do it there. The common endpoint of those two rays has a name. We call it the vertex. Now, you've probably heard this term before in math, especially when you're talking about parabolas or quadratics. And you can even talk about the vertices or a vertex of other types of functions like an absolute value, et cetera, et cetera, et cetera. So that's why it kind of feels natural to call the point where two lines meet and end the vertex. So if we have something that looks like this, and let me draw them in different colors. So we'll do red on the left, we'll do blue on the right, and they're meeting at the same endpoint. So the point at which they meet is called the vertex. The initial and terminal sides can be up to you, but traditionally in trigonometry, we would say that the blue one in this instance is the initial side, and the red one would be the terminal side. So an angle is formed by two rays with common endpoints. The angle is this right here. It's the measure of how much you're swinging from the initial to the terminal side. And you always go initial to terminal. Traditionally, most of the time, we're going counterclockwise. Now, this thing that I just drew, that's what we call the Greek letter theta. Let me draw that just a little nicer. So again, it's the measure of how much we're swinging from one side to another, from the initial to the terminal. And we call that value theta. That's our angle. It doesn't have to be theta. There's lots of other variables we have. We have lots of Greek letters, alpha, beta, gamma, zeta, kappa, you name them. But this is kind of like our x. Theta is very, very, very much like our x. So again, it looks like a 0, but with this kind of curly part in the middle of it. Let me draw it a little bigger. There we go. Some people will have it kind of extended past that. It's got all sorts of different variations, but that is theta. Think of it as our brand new x. So we like to use x in algebra senses. We tend to like to use thetas for angles, for a lot of trigonometric senses. And again, the terminal side doesn't have to be on the left and the initial on the right. They can flip-flop. It's just a matter of whether it's a positive or negative angle, as we'll discuss later. Okay. So this angle right here would be the same as long as I keep the relationship of the terminal side and the initial side together, but I could rotate them however I like, as long as if I'm rotating the terminal, I rotate the initial side in the same manner. So let me try and just demonstrate that by drawing it maybe this way. See, it's almost 90, so this looks pretty good. That's me trying to draw the same exact theta. So going from the initial to the terminal, that's the same. I just drew them in a different manner. Instead of drawing them like going up left and up right, I drew one of them going just barely up and right and the other one going down and right. But how much we're swinging from one to the other is exactly the same in these two pictures. So there's literally infinitely many ways that you can draw an initial and a terminal side to represent the same angle. But that can create a little bit of chaos because we want consistency. We want to have some, well, standard position so that we can better understand the size of the angles, what they look like. What does 130 degrees look like? What does 270 degrees look like? What does 300 degrees look like? What does 85 degrees look like? So we need some kind of standardization. So our standard position has the vertex at the origin. And when I say origin, I mean of a standard rectangular coordinate system, or Cartesian if you know the fancier name for it. So the vertex will be the origin. So the point at which those two lines meet will be the origin. The initial side will be on the positive x-axis. The terminal side goes wherever it ends up. The terminal side will go wherever it ends up. So I'll leave that little memo, but we're going to try and draw that same set of angles. So let's do black for our axes. That's not perfect. Let me do a little better than that. I think I mentioned before that I'm using a drawing tablet that I can't actually look at while I'm writing. So doing things straight is quite difficult, even with a ruler, in fact. So there's our standard coordinate system that you've used over and over and over and over and over. But our initial side is going to be on the x-axis. Then we said the vertex is on the origin, so there's the vertex. And the terminal side is just where it ends up. So this is going to go a little less than where the y-axis is. So again, it may not be perfect, but just assume I'm trying to draw it to demonstrate that it's the same. So this angle, this amount of space between them, and again going from initial to terminal, would be the same theta as before. So again, all three of those pictures are representing the same angle of measure between an initial and a terminal side. Drawing them this way or that way is fine, but drawing them this way is going to help us be more consistent and more understanding of the material. So this is how things are generally going to go. Now, I've mentioned that the initial side doesn't have to be over here and the terminal over here. They can be swapped. You can, if you really, really want to, say that the initial side is here and that the red one is going to go below. So it's a matter of whether you want to rotate clockwise or counterclockwise. Positive angles rotate clockwise. Excuse me, I was about to say that incorrectly because I'm looking at the next one. Positive angles rotate counterclockwise. So we're starting here and we're swinging up. We're swinging up and then left and then down and then right. So again, this is the direction that we're swinging for a positive angles. For a positive angles, I just combined single and plural. Negative angles are if you were to swing the other way. So if I did this instead, oops, a little squirrely. So X, Y, let's say we still, and you still always have to have the initial side on the X-axis. That's always true. The initial side must go on the positive X-axis, not the negative, the positive. How do you know the difference? Negatives are on the left, positives are on the right. So now instead of swinging counterclockwise, I'm going to swing clockwise. So about there, roughly. So now we're swinging clockwise, but this angle right here would be opposite to the ones before. So let's just throw a random number out there. Let's say that this angle for the first three images I drew was 85 degrees. So this right here would be 85 degrees, which means this would be 85 degrees, which means this would be 85 degrees. We'll talk about what a degree is soon, if you don't know. But this right here, because we swung clockwise instead of counterclockwise, this would be counted as negative 85 degrees. And again, I'm not declaring that's what they are. They're in the ballpark. But again, if this is 85, this is 85, this is 85, but that makes this negative 85 because of swinging in the opposite direction, if you will. We will more often swing counterclockwise to get positive angles than clockwise to get negative angles. We more like to deal with positive than negatives. I think that's just true of everything in life. We want positive money, we want positive growth, we want positive angles. But that's not to say we can escape the negatives all the time. We say that an angle lies in a specific quadrant based on the terminal side. So you should have heard of quadrants in the past. Very, very quickly, and just with the abbreviation of Q, the top right is supposed to be quadrant 1, the top left is supposed to be quadrant 2, the bottom left is quadrant 3, and the bottom right is quadrant 4. And if you had algebra teachers who don't like to explain why things are, which is very common, you probably wondered why you didn't go 1 here, then 2 here, then 3 here, then 4 here, or maybe go 1, 2, 3, 4. Why were they going counterclockwise and starting in the top right? Here's the reason. Because when your initial and terminal sides are on the positive x-axis, when they're the same line, we call that 0 degrees. And as that terminal side, as the red one, swings, we go to 1 degree, 2 degree, 3 degree, 4 degree, 5, 6, 7, 8, 9, 10, blah, 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 until we hit about 90 degrees. So from 0 to 90 degrees is in quadrant 1. Then as we keep swinging counterclockwise, we go to quadrant 2. Then eventually we end up quadrant 3. Then eventually we end up in quadrant 4. The entire labeling of quadrant numbers is based on trigonometry and positive angles as they go from 0 all the way up to 360, or even more if you keep going around more. So this angle that I've drawn here as a positive angle, this would lie in quadrant 1. I'm going to erase this in just a second. But that would be an angle in quadrant 1 because its terminal side is in quadrant 1. However, when I did it as a negative angle, as a roughly negative 85 degrees, this would be in quadrant 4. Now that doesn't say that you can't have a positive angle in quadrant 4 because I could have swung through quadrants 1, 2, 3, and then got to 4. And we're going to talk about that idea very shortly. So again, that first image is in quadrant 1, this other one is in quadrant 4. I don't really want to make that statement about the two up here because they're not drawn in standard position. So that's another benefit of standard position, is that we can talk about what quadrant it's in, and a lot of the math in trigonometry is based on the quadrant. Spoilers, there's this rule called a smart trig class that ASTC tells us some of the positives and negatives based on what quadrant we're in. All right. This is something that we'll discuss numerously throughout the semester, constantly throughout the semester. What is a quadrantal angle? Well, a quadrantal angle means that the terminal side lies on an axis. It could be the x-axis or the y-axis. It could be the positive or the negative of said axis. These are very important to understand, that a lot of the basic principles of memorization, they work differently for quadrantals than, say, 30 degrees or 60 degrees or 45 degrees. 90 degrees, some of the features of it just are different. And again, I'm really jumping the gun and doing a lot of foreshadowing here that, you know, maybe I shouldn't do, but I like to. So if an angle ends up lying on one of these axes, it's kind of a special case. It doesn't mean that a lot of things are different, but you have to understand the different aspects of it. So you've heard me say 85 degrees numerously now. What exactly is a degree? Well, it's one of the ways to measure an angle, kind of like feet is a way of measuring distance, kind of like degrees Fahrenheit is a way of measuring temperature, or degrees Celsius is a way of measuring temperature. And I chose that one intentionally because they're not related at all. Degrees, in terms of an angle, have nothing to do with degrees and temperature. It's another one of those, the word has two kind of definitions. So don't think that just because I say the word degrees, I'm talking about temperature. In fact, as a mathematician, when I want to talk about the temperature outside, I don't just say it's 90 degrees, I'll say it's 90 degrees Fahrenheit, because 90 degrees isn't well labeled, and it would make you think, oh, it's a right angle outside. That's the temperature. Wait, that doesn't make sense. So I hope that you have kind of been accustomed to some talk in the real world. You talk about people doing a 180. That means that they turn around. You know, they were moving forward and now they're moving backwards, or they were moving left and now they're moving right. Or maybe you've heard of someone talking about going a full 360. That's not turning around, that's turning around completely and facing the same direction. It's one complete rotation or revolution, if you will. So 360 degrees means that we've gone all the way around the entire system. So let's say we have our initial side here, and I'm going to kind of try and put it on the top of that. And then our angle goes all the way around through quadrant 1, 2, 3, 4, and then ends up on what we would have normally called 0 degrees. So that means that our initial and terminal side are actually the same. They should be drawn on top of each other, but then they're going to cover each other up. So I'm just trying to kind of superimpose them by like a millimeter off of each other. So that angle right there, again, this little circle, that's not a circle, that's just demonstrating that we rotated all the way around. That would be 360 degrees. Please, I'm going to erase these arrows in a second. Please, please, please do not ever forget that. If you are talking about an angle in degrees, you have to have that little 0 looking exponent. That is not a 0 exponent, that is a symbol, in the same way that we write FT to symbolize feet, or the same way that we write L cubed to describe a cubic liter, a measure of volume. So this is not an exponent of 0. That does not mean that this is 360 raised to the power of 0, which would be 1. This is just a new symbol. So that's the degree symbol. So if you start at the positive x-axis, rotate through quadrant 1, 2, 3, and 4, and then stop at the same line, that's 360 degrees. If you keep rotating, you'd be at 361 degrees, 370 degrees, 450 degrees, 540 degrees, 545 degrees. Eventually, if you go around 2 full circles, that would be 720. If you do 3 full circles, that would be a 1080. Maybe some of you are into sports with boards involved and you talk about them doing 540s and 720s and 1080s and things like that. So that's because they're doing 1.5 or 2 or 3 full rotations or revolutions, same word. If you have a test problem that does not have the degree symbol built into it, or a homework problem, if it doesn't have that symbol built into it, then you would have to make sure you write it. When you're showing your work for your test that you have to submit, you have to make sure that you're writing this. Now, am I going to take points off if it's missing on 1 or 2 spots of your work? Honestly, probably not if you have the answer right. If it's missing everywhere, that's another story, and that's when I'll start saying you need to be better at your symbols. Because guess what? If you don't write that little circle, if you don't write it, you're saying that it's something called radians. If it's just a number written, it's 360 radians, and that is something completely different. Let's pause on that, though. A couple of basic geometric definitions you may be a little rusty with that we'll use quite often in here. Any angle that is less than 90 degrees, I should say any positive angle less than 90 degrees, we call that acute. Oh, look at the cute little angle. It's a cute little angle. Sorry for the silliness, but that's how I remembered it as a kid. It's small, it's acute. A right angle, it's not that it's correct, it's just a name for 90 degrees. We will say that term 10,000 times throughout the semester. We love right angles. We love them. We love right angle trigonometry because it simplifies things. Obtuse, and I don't mean like obtuse as in being dense. Obtuse, I have a word that I associate it with it, but it's just one of those things that I don't want to put it in a recording, so I'm not gonna. If I was in a classroom, I'd say it, but it's not bad. I just don't want to say it. I don't like things being recorded. I really don't. And then someone comes back 5 years later and I get canceled because of it. You know what I'm saying? Sorry, again, I have a silly sense of humor. So obtuse, think wider. Obtuse, so that's between 90 and 180 degrees. So an acute angle, and I'm going to skip the, well, no, I'm not for now. I'm going to skip doing the colors eventually. For now, I'll keep doing it. I'll also skip drawing the arrows eventually. So this would be an acute angle. Spoilers, if something's written in standard position, all acute angles end up in quadrant 1. These will always be in quadrant 1, in standard position. Because 90 degrees is the positive y-axis. I'm going to label all those quadrantals shortly. A right angle is 90 degrees, which I just mentioned. So initial is blue, terminal is red. So there's our right angle, our 90-degree angle. An obtuse angle is something between 90 and 180. So that means it's in quadrant 2. So if your initial is here, that means your terminal is somewhere over here. So this could be like 130 degrees, 170 degrees, 141 degrees. That is an obtuse. All right, and since I didn't label it up there above where it said quadrantals, let me just come down here and make a little memo. Oh, it's a page break, that's why. I'll give you a second to finish writing that stuff first. And I'm gonna mute because I got a cough bad. All right. Cool. And remember, if I ever go too fast, if I'm going super fast, someone can speak up and I can scroll back. But if it's a matter of, I just went a little too fast, you can always catch the recording. Yeah. So what are the quadrantals? So someone just asked, is a right angle in quadrant 1? And I'm going to say yes and no, kind of, maybe, sort of. And I'll describe why that is as soon as I finish these drawings. Oops, that was a little wide. And I'm going to skip doing the X and the Y's. So I think I was doing initial for blue and then red for terminal. So that would be 90 degrees. That's your first quadrantal. Let me describe the swing. There we go. The second right angle, I'm sorry, the second quadrantal will be initial here and then terminal here. So we have swung from the positive x-axis over to the negative x-axis, and that is 180 degrees. That's our turnaround. Also known as a straight angle. You can see that definition down there. Then we have our, oopsies. Oh, I said I wasn't going to label that anymore. Blue here, red here. So this would swing through quadrants 1, 2, and 3. So that would be 270 degrees. Every quadrantal is a multiple of 90. Spoiler if you haven't figured that out already. And then the next one, which we've already basically mentioned, where your initial and terminals are on the same spot. Initial, we rotate our full 360 degrees. Terminal. So this is 360 degrees. Comma, and I'm putting the comma in front of it, because guess what? If you don't rotate all the way around, it's also 0 degrees. If your initial side is here and your terminal side is here and you haven't swung at all, that's 0 degrees. It's also a quadrantal. So 0, 90, 180, 270, 360. Every multiple of 90 degrees are quadrantal angles. So to answer the question asked previously, is this 90-degree angle in quadrant 1 or is it in quadrant 2? The answer technically is neither. It is not in a quadrant because it is on the dividing line of the quadrants. It's between quadrants 1 and 2. So you can't say that quadrantals are in a quadrant. They are separated by 2 quadrants. 180 degrees is separated by quadrant 2 and 3. 270 degrees is separated by quadrants 3 and 4. 0 or 360 or 720 or 1080, etc. They're separated between quadrants 1 and 4. So that was an excellent question. Okay. Give you about 20 more seconds to finish drawing those. And let's do this, leave some space there for my drawing. Okay, so a degree is one way of measuring an angle, and it is generally most students' favorite version of measuring an angle. But it's not the only way to measure an angle. And in fact, sometimes we can't use it. There are times when you can always, I don't want to use the word always there. There are times when you can use degrees, but there's also times when you can't. The cool thing is with radians, you can always use them. And we're not ready to talk about the why and when we can and can't use either one. Radians are always usable. Degrees are usually usable, just so you know moving forward. And we'll talk about when you can and can't, when it becomes necessary. So the other type of thing, so we have degrees Fahrenheit in temperature, and we have degrees Celsius in temperature. Yes, we also have degrees Kelvin, but no one uses Kelvin because none of us are measuring things that are super, super cold. Otherwise, what's the point? You have feet, you have meters. They're both units of distance, but one is the SI system and one is the metric system. Heck, we have different units of measurement in a single system. We have feet and we have miles. So a radian is to a degree like a foot is to a mile. They're just two different ways of measuring things. I don't mean that it's a ratio of 5280 between them. There is a ratio between them though, and we'll talk about that shortly. So a radian is a second way to measure an angle. When you're talking about radians, you do not have that little exponent 0 thing, that symbol that symbolizes degrees. So something that's in radians, again, does not have that little 0. Also, when we are dealing with radian angles, almost always, I'm willing to say 98, 99% of the time, there's going to be a pi somewhere in there. And you're not going to write the letters pi for pi. You should use the symbol. It's just when I typed these notes, Word was being a pain in the butt. And it didn't want to put the symbol in there. So a radian is a second way to measure an angle. 2 pi is 1 complete revolution. So for radians, 2 pi is now a complete revolution. So if in degrees, 360 degrees is 1 complete revolution as seen here, that means that 2 pi is the same thing. So 2 pi is the same as 360 degrees. That's our jumping off point that we'll see. But before we get into that aspect, let's actually try and understand what a single radian is by definition. So this is a definition. This isn't something that you could just deduce. The definition of a radian is that 1 single radian, so 1 feet, 1 mile, that kind of thing, 1 radian, is the angle that makes the outer length of a circle the same as the radius. So let's draw up a circle. Let's draw up a circle. And here's the center. And let's have our initial side be here. And I'm going to label that R for the radius. So that's the radius of this circle that I just drew. Then my terminal side, in order to make this happen, it has to be about here. You just got to trust me that it's about here. Now, if that's the radius, this has to be the radius because the distance to the center to the edge of a circle is always the same distance, the radius. So this distance is the radius, so this distance is also the radius. And the idea is that 1 radian, so radian kind of sounds like the word radius, right? I bet there's a reason for that. It's the angle that is formed that makes the outer length of the circle. So in, let's go with orange. This distance, this curvy, this bendy distance right here, this arc is actually the official name. This arc is exactly the same as the radius. So in other words, if this blue distance was 5, the red distance would be forced to be 5, and a radian is this specific angle so that the distance along this arc would also be 5. So again, that was just a random example. If this was 5, that means this is 5, and this is 5. All of those distances would be the same. 2 of them are straight, 1 of them is bendy, 1 of them is an arc, the arc of a circle. So right here, again, swinging in this direction, that angle would be 1. It's just the number 1. When you don't write units, you assume that they are in radians. And you might say, well, Mr. Beckner, I had you for pre-calc 1, and I had you for quantitative reasoning, and you said always write units. Well, the thing with trigonometry is you see these things so much, it is a basis that you don't write it. Kind of like when you have a coefficient of 1, you don't write it. Kind of like when you have an exponent of 1, you don't write it. Kind of like when you have a square root, you don't write the 2. It's something that is used so absolutely freaking much that you don't want to have to write radians or RAD every single time. It gets extremely tedious. That is a major point to understand day 1. Degrees are not the same thing as radians. Degrees, you have to write that little circle, that tiny little circle as an exponent so you can tell it's a degree. Because if I do this, pay attention to where I am. If I do this, now that's in degrees, and this is no longer true. That angle is not 1 degree. It's much larger than 1 degree. It's more like 80-some degrees, 70-some degrees. Sorry, I got distracted at home. Give me about 20 seconds. Okay. Sorry about that. Dog issues. And actually, I just realized that the numbers I was saying was too high. It's not 80 or 70. It's more like 60. Yeah, it's like 60. So I drew that a little too, the red is a little too high, but don't worry about that. This is not a diagram I'm going to expect you to understand and know. But what is good to know, let's do this again. A little oblongated pronunciation is important. Circle. So let's have our initial side be here. Terminal side be here. Again, the center was obviously in the center. This would be 180 degrees because it's a straight line. We've swung from the positive x to the negative x-axis. So this would be 180 degrees. In degrees, but in radians, it's pi. Why is it pi? Because 2 pi is 1 complete revolution. This is half a revolution. So here's the image of the complete revolution. Center, initial, rotate all the way around 360 degrees. Terminal, like I said, I'm not going to draw those arrows all the time. I generally don't do it anymore unless it's necessary. So that angle, I drew the circle a little too much out. This is the angle. There we go. Kind of looks like a bullseye. That angle, because it's a full revolution, is 360 degrees, but in terms of radians, it's 2 pi. You've seen 2 pi in some formulas before, some geometric formulas. C equals 2 pi r. Circumference is equal to 2 pi times radius. You know how the number pi was established? Someone wanted the ratio of the circumference and the radius. That's how pi was established as a number, that 3.1415927 something, blah, 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 blah. You only need to know it to 3.14 as an approximation, but we generally don't even need that. So pi as a number is 3.14, which means this is 3 radians and just a little more. This is 3.14 radians if you go from 0 to 180 degrees, if you go half a circle. If you go all the way around, that's 2 pi. 2 times 3.14 is 6.28. So if you wanted just a decimal approximation. So 360 degrees is about 6.28 radians. It's exactly 2 pi radians. But again, just if you wanted a more tangible number for that. So it's these two statements, either one, that gives us the ratio that we can use to convert from radians or degrees, which we'll be doing constantly throughout the semester. So we said a full circle is 360 degrees, which means 360 degrees is 2 pi radians. Or you could use a simpler version of that without the 2. Half a circle was 180 degrees, and that was just a single pi. So 180 degrees is pi. This is the better one to use for your conversion process because it's just smaller numbers. It's less numbers. So that tells us, if you understand the concept of dimensional analysis, if you have a unit conversion like 180 degrees is pi radians, that means to go from one to the other, you're just multiplying by those things as a fraction, one on top of the other. It's just the which one goes on top and bottom is dependent on what you're starting with and what you're ending with. Here's what I always like to say, and I'm going to add this. Out with the old, cancel, units, new. If you're in degrees starting out, that means your multiplier needs to have the degrees value in the bottom so that those things would cancel top and bottom. If you're starting out in radians, then you'd need the pi radians in the bottom so that the units of radians cancel, leaving you with degrees. I'll even show you what this would look like if you did it wrong one time, because you might be a little rusty with your dimensional analysis. Another shortcut, I almost call it a cheat because it really simplifies things. Like I said earlier, 98, 99% of the time, if you're talking about radians, there's a pi somewhere probably. So if your original number has a pi, you're going to need the pi in the bottom to get rid of it because we generally don't see pi in degrees. So if your original number doesn't have the pi, then you probably need the pi in the top so you end up with it, and you don't get it in the bottom. I'm trying to decide if I want to keep with the definitions. Let's go ahead to examples. Just give myself some space. I'm going to leave this up here. So finally up to some examples today. Example 1 will be converting to radians. And for A, we're going to have 30 degrees. Terrible looking 0. Let's try that again. I am going to do this right, and then I will do it wrong, and I will erase the wrong version afterwards, but let's do it right. So we got to multiply. We're in degrees, we're converting to radians, so we're going to multiply by a fraction with those conversion factors, one top, one bottom. It's either pi over 180 or 180 over pi. So because we're in degrees, we're converting to radians, we need the pi in the top and the 180 in the bottom. I usually don't write the word radians as I've already described, so I'm just going to do pi over 180 degrees, but I will always write the degree symbol. That's forced. And in fact, I meant to write equals and then do the multiplier. Let me just start over. Sorry. 30 degrees times fraction. Nothing I did was wrong. I just wanted an extra step written. And then the pi over 180. So when you do this, 30 and 180 reduce. You've got to know how to reduce your fractions. 30 would go into 180 6 times. But the bigger number's in the bottom, so that means the 6 is going to go in the bottom. So there's a degree in the top, there's a degree in the bottom, so those units cancel each other out. I'm going to erase the canceling, but they will cancel each other out. So there's no more degrees. The 30 and the 180 reduced to a 6 in the bottom. The pi, there's nothing to cancel it, so we keep it where it was. So the answer is pi over 6. Pi over 6 radians if you want to write the unit, but I just say pi over 6. Again, without the degree symbol, it's a perfect assumption. There we go. B. Oh, no, I said I was going to do it wrong first. So, and actually I won't erase it. If you took your 30 degrees and you multiplied it by, red for wrong this time, let's do 180 over pi. So first of all, now the 30 and the 180 are being multiplied, so 30 times 180 is going to be 5,400. The degrees of this one are on the top, the degrees on this one are on the top, and if you add feet times feet, you get feet squared. So a degrees times a degree is a degree squared? What in the world is that over pi? You are never ever going to see an angle that looks like 5,400 over pi in here. Just trust me. But the units, if you pay attention and you process things accurately like a pre-calc to calc student should be doing, then you would see this just goofy mess that says no, bad, stop, redo. All right. I looked at the time and I thought our class was done. I was like, there's no way it took us an hour and 15 minutes to get this far. It throws me off that our class starts at 12:30. That's all. Next up, let's do 60 degrees. I'm going to do a lot of ones that you'll see over and over throughout the semester. So we know we're going to multiply by a fraction. And we're going to do it right every time from now on. So you might say, all right, well, we did pi over 180 last time, so I know what it's going to be for the rest of this example. But don't just know how to do something consistently. Know how to do it if you're going back and forth. Why is it that we're multiplying by pi over 180? because this has degrees in the top, so we have to have the 180 degrees in the bottom to cancel those units, forcing the pi to the top. 60 and 180 reduce. 60 goes into 180 3 times, which means the bottom is now a 3, the 60 is gone. So you could put a 1 here if you wanted, but since the pi is still on the top, you don't need to. So that's the answer, and I meant to do that in black. So 60 degrees is pi over 3 radians. C, 45 degrees. 30, 60, 45. These are 3 of the most used angles throughout this course. You will see them in radian format constantly. And a lot of students don't like doing the math in radians, so in their head, they just convert them to degrees. They may not show it, they may show it. It's up to you. But the important aspect is knowing how to go between one and the other. So we're in degrees, so we know degrees goes in the bottom to cancel. We know the pi goes in the top to fix everything. 45 will go into 184 times, so that's a 4 in the denominator. The degrees would cancel each other out, and the pi is still in the top. Let's do D over here. Ooh, I might have a hard time getting all of those up here. That's all right. Squish it in just a little bit. That's why I didn't want to have the wrong bit over there, but it's okay. I want to leave it. It's good to see. For D, 90 degrees, another extremely popular angle that we'll deal with all semester long. So we multiply by a fraction. Oh, I forgot to do the equals. By a fraction, clearly pi over 180. With the old and with the new, 90 and 180 would reduce to half. Pi stays in the top. So pi over 2 is the answer in radians. So 90 degrees is equivalent to half of pi. I feel like that one makes sense because 180 degrees is a full pi, 90 is half of pi, pi over 2. I'm going to try and squish this in here. E, 120 degrees. Popular, but not as popular as the rest. Multiply by pi over 180. Degrees. 120 and 180 will not divide perfectly, but they will reduce. 60 goes into both. 60 goes into 120, excuse me, twice. 60 goes into 180 thrice, or 3 times. The pi needs to stay in the top. There's 2 ways you can write this. You can write the pi in the top or to the side. Both of those are accurate answers. F, last one for this example, 135 degrees. So we're going to multiply by pi over 180 degrees. The degree units cancel. Let's see, 45 is going to go into both of these. And you can reduce them slower, but I do suggest trying to reduce them with as big of a number as possible. You could say, all right, 5 goes into both of these, and then 9 goes into both of them. Or 3 goes in, and then 3 goes in, and then 5. However you're reducing, just get the job done completely, because if you don't reduce completely, your answer is wrong. Now, in bigger problems, a non-reduced answer could get you partial credit, but if I gave you an example like this on a test, I would not give you credit for a non-reduced answer. And that brings me to a very important point. These are not test questions. These are not test questions. These are not test questions. This is like 1 + 3 for us. This is something that you need to be able to do every day, every week, every month of the semester. I will never give you a test question where the whole goal is just to convert this. And I'll explain what students do wrong in that regard when it becomes relevant in a few classes, maybe next class. All right, so 45 goes into 135 3 times, into 180 4 times, so that's 3 pi over 4, or 3 over 4 pi. I'm not going to write it the other way. You can drag it to the side if you like. It's up to you. Let's go the other way. Let's convert to degrees now. I'll give you a second to finish writing. And we're going to start with pi over 3. And some of you may be clever and say the answer is 60 degrees. Look at B. The answer is pi over 3, so we know it's 60 degrees. Show your work, though. Let's prove it, because it's going to be important to be able to do this later, after we've learned 50 million other things. So we take the pi over 3. Now, because I don't see a degree symbol anywhere, I know it's in radians. Also, because I see a pi, I'm pretty sure it's in radians, just without even knowing the other issue, times fraction. So this is where you go, do I multiply by pi over 180 or 180 over pi? Well, if you put the 100, I'm going to do this wrong for a second. I will erase this one. If I put the 180 degrees in the bottom, the units in the bottom, which means this would be per degree, and that doesn't make sense. Having degree as a unit in a bottom doesn't make sense, which is why that makes that wrong. The major clue for me, and what it probably will be for you, is out with the old. I see a pi in radians. You generally don't see that answer in degrees. So the pi is going to be in the bottom, meaning the 180 goes in the top with its degrees. 3 will go into 180 60 times. The pi's will cancel each other out. So again, 3 goes into 180 60. So that's 60. And now because I see a degree, I didn't cancel it anywhere. That's our answer. And that's confirmed earlier. 60 degrees was pi over 3, so pi over 3 better be 60 degrees. Let's do as many as we did last time. Let's go with, next up, pi over 4. So we multiply by pi over 180, right? Let's show you what this would look like if you did pi over 180. Let's actually show you. Pi times pi is pi squared. 4 times 180, well, 2 18s is 36, 2 36 is 72, so that's 720 degrees. So the answer is pi squared over 720 degrees. What in the world does that mean? My head just exploded. I had an aneurysm. So that was wrong, 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 wrong. So even when you do things wrong, if you're being monotonous and careful, meticulous and not monotonous, you might feel it's monotonous, but if you're being meticulous and careful, you can show why your answer doesn't make sense. So it's really supposed to be 180 degrees over pi. 4 will go in 180 45 times. The pi's will cancel each other out, top and bottom. We have our degrees now, so that's 45 degrees. Five pi over 3 for C. Oh, that was not what I expected to happen. You hit enter after something and it makes it go down. Word makes great sense sometimes. Am I right? So we take our 5 pi over 3. That's an ugly 5. No, not select. What's happening? What's going on? There we go. Okay. Times. And we know the rule now, 180 degrees over pi. 3 goes into 18 6 times. So that's 60. The 3 and the 180 reduces to a 60. And then you can say that 60 times 5 is 300. So this would be 300. The pi's will cancel, and you'll have your degrees in your answer. You could have multiplied first. You could say 5 times 180 is 900, and then 3 goes into 900 300 times. It's up to you. You can multiply, reduce, and whatever you like with fractions. D, 7 pi. Ooh, ugly pi. Okay, an ugly pi is still a tasty pie, right? So we multiply by 180 degrees over pi. The pi's will cancel. You'll be stuck in degrees. 7 times 18 is what, 126. So tag on the extra 0. That's 1260 degrees after the pi's cancel. You don't have to be lightning fast like that with your arithmetic. but you should be capable of doing arithmetic without a calculator. Remember, tests 1 and 2, not supposed to be using them. E, let's go with 3 pi over 2. So you multiply by 180 degrees over pi. 2 goes in 180 90 times. 90 times 3 is 270. Pi's cancel, and you're left with your degrees. 5 pi over 18. Last one. We take our 5 pi over 18. We multiply by 180 degrees over pi. 18 will go into 180 10 times. 10 times 5 is 50. The pi's cancel. So that would be 50 degrees. So that's how we go between degrees and radians, or radians to degrees. Again, this is just a very, very, very minor step in the bigger picture of most of the problems that we do, if you feel the need to convert them. So some students just learn the idea of everything in degrees. If they get a problem in radians, they'll just convert it to degrees so they understand the size of it. Some people actually eventually learn a lot of the different radians and memorize them. Oh, 60 degrees is pi over 3. 30 degrees is pi over 6. 45 degrees is pi over 4. Those are very important. I would encourage you to memorize 30 is pi over 6, 60 is pi over 3, 45 is pi over 4, 90 is pi over 2, 180 is pi, 360 is 2 pi. It'd be really good to know 3 pi over 2 is 270 as well. Those are all extremely important and will be seen over and over and over and over and over. You're going to see pi over 3 all semester long. You're going to see pi over 4, pi over 2, pi over 6, 3 pi over 2 all semester long. So please take the time, make the effort to memorize those. Okay. Next topic, coterminal angles. This is something that we've already actually introduced, believe it or not, with 0 degrees being the same thing as 360 degrees, but it's not just those two that are the same. There's actually infinitely many angles that are equivalent. I'm not saying that all angles are equivalent. I'm saying that 1 degree has infinitely many other angles that are equivalent. 1 degree is the same as 361 degrees. Negative 1 degree is the same as 359 degrees, is the same as 719 degrees, is the same as 1079 degrees. I think I said that right. Because when you're talking about going around that circle, once you make a complete revolution, you're back where you started. And then if you go another 30 degrees to say 390, you're at the same location as 30 degrees. And for most of the things that we do, almost everything that we do in this course, it doesn't matter how many times you go around in a circle because you keep ending up at the same spot. So 30 degrees is the same math, the same trigonometry as what you would get if you did it with 390 degrees. Negative 45 degrees would be the same as 315 degrees. 315 would be the positive version of the angle. Negative 45 would be as if you rotated clockwise instead of counterclockwise. Draw those up really quickly. And again, I'm not always going to use these colors moving forward, but here is approximately 30 degrees. But it's also, so that's if you just go that little bit, or you could go all the way around and then to that line, if I just extend it a little more for drawing's sake, that would be 390 degrees. Any of the actual trigonometry we do with 30 degrees will lead to the same answer as if we'd done it with 390 degrees. But we don't want to memorize all these different patterns for 390 and 420 and whatever, for 540 degrees, all those different ones. So when you get these big, big, big angles, we generally like to turn them into something between 0 and 360 to be able to process them. And in fact, most of the time, if we have something like 300 degrees, we're going to try and turn it into something between 0 and 90 using some tricks. But we'll get there another day. All right, initial here, terminal, we're going to go with negative 45 degrees, which would be there. So here, if you rotate this way, that's negative 45 degrees, but it's the same as if you'd gone counterclockwise instead, and that would have been positive 315 degrees. So coterminal angles have the same initial and terminal sides. And the way you can get between one coterminal angle and another is just add or subtract 360 degrees. As many times as you need to show they are the same or to find another coterminal angle. Some examples. What do we got? 15 minutes. How much is left of this? Not very, in fact, that last little bit we're not going to be covering because it was removed from the material. Perfect. Sorry, back to where we were. And again, if that doesn't make sense to you, just stand up and don't move at all and think about what direction you're facing. Then do a full rotation, a full 360 degrees, a full 2 pi radians, and notice that you're looking at the same position. Nothing's really changed. Or have yourself rotate 90 degrees and then rotate another 360 degrees and you'll be facing the same position. Nothing's really changed. Spinning yourself around 360 degrees, either clockwise or counterclockwise, doesn't change anything in terms of trigonometry. All right, example 3, I believe. We are going to find a coterminal angle in the range coterminal, I can spell, I just type too fast sometimes. I can't always spell, admittedly. And I'm going to put this in degrees. Let's go 0 less than or equal to the angle less than 360 degrees. That's a terrible looking less than. Let's redo that, make it a little prettier. There we go. A, we're going to have 410 degrees. So maybe I'm asking you to do some trigonometry with this, but you haven't really studied 410 degrees very much. So it would be best to just add or subtract 360 this until you get it in the range of what you have studied more extensively. So what we can do is take the 410 to get it between 0 and 360. Well, I think it's obvious that you would need to subtract 360 degrees. And I will fix my degree symbol there. 410 minus 360 is 50 degrees. And you only had to do it once. So that's your answer. B, negative 22 degrees. So that's a negative angle, something that sometimes we like them, sometimes we don't. So let's just make it a positive angle in that, you know, kind of standard 0 to 360 degrees. Well, it's negative, so we should probably be adding 360 degrees. And negative 22 plus 360 is 338 degrees. There we go. C, 999 degrees. Well, if you just subtract 360 once, sorry, hold on, distractions. Okay, if you subtract 360 once, let's see, 990 minus 360, 936, so that's 639. That's not good enough. So what you have to do is subtract again. And if you subtract one last time, 639 minus 360 is 79 degrees. There we go. And that's in the window we want. Last one, we'll make this the trickiest, 9 pi over 2. Not even going to start out with the simple one in radians. We're going to do a complicated one in radians. All right, so 0 to 360 degrees means that we need to be between 0 and 2 pi. So this would be the same thing as saying 0. I forgot my degrees over there on the first 0. It's still technically correct because 0 degrees is 0 radians, but I want to make sure it's accurate. So this would be the angles between 0 and 2 pi radians. Notice that I had the or equals on the 0, but not on the 360. Same for this version. And that's because these two are the same. You don't want to have two representations of the same. So doing it this way is every possible angle. So we're supposed to be subtracting 360 degrees, but in terms of radians, 360 degrees is 2 pi. So we got to subtract 2 pi. Well, guess what that means? We got to get an LCD. 2 pi is the same thing as 2 pi over 1, FYI. The LCD between 1 and 2 is 2. And we will be doing this all semester long, so if you're rusty with fractions, go practice it on your own, go find your resources. Unfortunately, that's not what we're here to teach. So the 9 pi over 2 minus, that already had the LCD, so it didn't change. For the other one, the blue 1 will go into 2 twice. 2 times the 2 pi will be 4 pi. So 2 pi over 1 is the same as 4 pi over 2. If you reduce it, you get the same thing, and you can see that that's fine. All right, so 9 minus 4 is 5. Now that we have a LCD, 5 pi over 2. Is this okay or not? Well, you should be able to tell. This 4 pi over 2 is the same thing as 2 pi. This is 5 pi over 2. 5 is bigger than 4, so this is still too big. So we take our 5 pi over 2 and we subtract another 2 pi, which I'm going to go ahead and write as 4 pi over 2. There's no reason to reinvent the wheel. 5 minus 4 is 1, so that's a single pi over 2, aka 90 degrees. So here's the thing. If you hated that, what you can do instead, and I don't care if you do it this way, but you have to know one of the two ways, you could have converted the 9 pi over 2 to degrees by multiplying by 180 degrees over pi. Then you would have whatever it is in degrees, I don't know off the top of my head, doesn't matter, and then you just subtract 360 degrees, and then you subtract 360 degrees again, and you'd end up with 90 degrees there. 720, so that means this was 810 degrees, not that it ultimately matters. So if you convert this to degrees, you should get 810, subtract 360, then 360 again, and you'd get 90. But here's the thing. If my math lab gives you a homework or test problem in degrees, it probably wants the answer in degrees. If it gives you a homework or a test problem in radians, it probably wants the answer in radians. So if you wrote 90 degrees for this, most of the time, my math lab is probably going to mark it wrong, and you're going to be mad at yourself because you didn't do that last conversion process. So that's why I say you can do that, but I didn't write it down because it's a longer method and it leaves more wiggle room for mistakes that we don't want you to make. All right, a couple last minute features. First of all, I'm actually going to point out this. To find complementary and supplementary angles of something, two complementary angles add to 90. So if you know one, you're going to do 90 minus it to find the other. For supplementary angles, they add to 180 degrees. If you have a hard time remembering that, they're in alphanumeric order. 90 comes before 180, C comes before S. Smaller number, smaller letter, larger number, larger letter. So if two angles add to 180, that means if you know one, you can find the other by doing 180 minus the first. If two angles are complementary, aka they form a right angle, that means they add to 90 degrees. So I'm going to draw those as a picture. So here, that's weird. Why did that happen? Okay. So here is angle 1. I'm going to do a little 1 to denote they're different. And then here is angle 2. These would be complementary angles because they add to 90. So if I knew the first one was 30, I could do 90 minus 30 to get the other one being 60. and certainly 30 plus 60 is 90. Supplementary angles add to 180 degrees, which means they form a straight line. So maybe your first angle is here on the right side, that's angle 1, and then here's angle 2. Since they form a straight line combined, that means they are supplementary. So let's say this bigger angle was 140 degrees. You do 180 minus 140, and that would tell you that this other angle has to be 40. And you could prove that because 40 plus 140 is 180. So those are pretty easy problems that will come up throughout the semester. We will need the complement and supplement of angles sometimes, and we'll get into the why and when then. Something that honestly we will not be studying in the rest of this course, I'm trying to highlight this without the drawings, but okay, you get the idea. Just pretend like I'm highlighting these two lines. This is an important concept, especially if you were going to go on to say physics, because it's the relationship between an angle, the arc length, and the radius. And it has everything to do with radians. When we said 1 radian was where its arc length was the same as its radius, and then the angle would be 1. So if these two things were the same, S and R, if the arc length and the radius were the same, then the angle would be 1 radian. If the arc length was twice the radius, that ratio would be 2, and it would be 2 radians. So using this formula, if you will, that an angle is the ratio of its arc length to its radius, that's the true idea of how we understand an angle in terms of radians. You can't do that in degrees. This process, this formula does not work in degrees. That's why we call it radian measure. So again, in the true basic definition sense of what an angle is, in radians, it's the ratio of arc length, which is that curvy distance along however much of the circle you're doing, to its radius. If you multiplied both sides by r, then you'd get this equation instead, that an arc length is the product of its radius and its angle, but only in radians. So this is what I was mentioning, that some things don't work in degrees. If you want to talk about arc length at all, you can't use degrees. You absolutely cannot use degrees. Okay, so that will close up 7.1. So we have finished the section. Don't worry about these last couple things. As I said, no longer available for us, necessary for us. You won't be tested on it. Shouldn't be any homework on it. So we finished our homework. We finished 5.1. I told you I'd do that. We finished 5.1 today. A week from today is September 2nd. So I already have that due date set up. 5.1 homework is due September 2nd by 11:59 p.m. Anytime I assign something, it's always due 11:59 p.m. Anytime we finish a section, it's always due 1 week later. And if any of you notice at the top of my save file, you can actually see that I edited my previous text version because I have it as chapter 7 here. So again, pardon the fumble there with calling a chapter a wrong number. It's going to happen again, I can guarantee it. But I'll do my best to do it as few as possible. So if you don't have any questions, we'll go ahead and call it there. It was great seeing all your wonderful faces, I suppose, besides that. And I say that because I'm not watching the video at all, y'all's videos, the couple of you that have it. So it's a little sarcasm, but again, I hope you learned a little something. Please take everything very, very serious about today, because most of this stuff is going to be an issue all semester long. Someone asked, would the initial angle ever be facing the opposite? They didn't say angle. Would the initial ever be facing the opposite direction? Is this what you mean? Like when we draw this up, are you saying would this ever be the initial and this the terminal? Is that what you're asking? No, it will never be that way. The definition we had earlier for standard position was that initial side is always on the positive x-axis. The terminal side is anywhere else. So I hope we cleared that up. Cool. All right, and I'll just leave this up here for a second. If anyone's interested in these two things, this linear speed is actually an extension of just that arc length we talked about. These are fun little formulas, but again, not going to do this at all. Won't test you on it. If there's one homework problem on it, don't be terrified of it. Try it, but again, I won't test you on it. So have a good one. Have a good weekend. We will see you on Monday. Take care, everyone. And this video will be up no later than 5 p.m. for the replay.